Hey everybody, today we'll look into an interesting inequality, and the inequality is called
Holder's inequality.
many of you were doing some functional analysis or any kind of analysis course. Maybe you have gone through this inequality before. So what I'll do is I'll kind of try to
Sketch the proof.
given in this amazing text by Krasik, an introduction to functional analysis. So if you want to look at the proof, you can actually refer to Krasik a bit by Krasik functional analysis. Okay, so what is this inequality about? So the inequality looks like this. So let me just write down the inequality. So if you have some kind of summation, and you have an absolute magnitude of two sequences, sigma and this one. So J1 till infinite is less than or equal to summation j to the power p, j1 to infinite to the power 1 by p, and then summation. So let's make it, let's make this a different index maybe. Let's make this, yeah, I mean, let this be j, and here I'm going to change this to m to q, 1 by q, and this is n being from 1 to infinite. Okay, so you have basically two sequences, this one and this one. Okay, so sequences means you have the first term, the second term, there's a second term, third term, and so on, goes on to infinite. You have the other sequence, this one, the 2, 3, and so on. And what you do is when you do this left-hand side, when you do the summation of the product of these two corresponding terms, take the absolute magnitude. This is bounded about by this quantity. An interesting inequality, it has a lot of applications. You use this in measure theory and various other places. So let's see how to prove this. The proof is interesting. When I looked at the textbook, it's a really interesting proof, so I just want to sketch it. So there's another, so what is P and Q, right? So P and Q are two numbers, two real numbers. It can be any real number PQ, says that 1 by P plus 1 by Q is 1, okay? So 1 by P plus 1 by Q is 1. Okay, now, how do we prove this? So we'll start with this. Interestingly, if you start with this one, these are two numbers, 1 by P plus 1 by Q is 1. So this is P plus Q divided by PQ is 1. Now, if I take this to the other side, P plus Q is PQ. Now what I'm going to do is I'm just going to, so this will imply PQ minus P minus Q is 0, right? So, well, what I'm going to do is I'm just going to add 1 on both sides. You will see what is the point of adding 1 on both sides. Now I'm going to just group the terms. So let's group this one. So what you get is P times Q minus 1 minus Q minus 1 is equal to 1. This will imply P minus 1 times Q minus 1 is equal to 1, right? You just factor out Q minus 1, it's a common term. And so you have P minus 1 times Q minus 1 is equal to 1. Well, that's interesting. Okay, now the next part is I'm kind of trying to prove another inequality. So the inequality, well, this is basically the main inequality which I'll be using to prove the Holder's inequality, which basically looks like this. So alpha times beta is bounded about by alpha to the power p divided by p plus beta to the power q divided by q, where p and q are these two numbers. Okay, and alpha and beta are any two positive numbers. Okay, these are just positive numbers. Well, they can be 0 as well. So if it's 0, it is actually clear that this is the case. For example, if I take alpha is 0, then the left-hand side is 0, is bounded about by this term is 0 plus beta to the power q by q, which is positive. Well, it is positive, so this is true. And the other case is when your beta is 0. When your beta is 0, The same thing, the left-hand side is 0, bounded above by alpha to the power p by p, divided by p, plus 0, right? So this is also true, right? So, well, for alpha and beta 0, the inequality is trivial, right? So we'll consider the case when alpha and beta are positive, strictly positive. And to prove this, interestingly, the textbook draws two graphs, right? So what are these graphs? So the textbook kind of tries to draw this function t to the power q p minus 1, okay? Where t is a variable, t is just some variable, t to the power p minus 1 is kind of trying to draw this graph. And the graph looks like this. The graph is increasing, okay? It's just increasing. And so this is u is equal to t to the power p minus 1. So your x-axis is t and your y-axis is u. Now, I need these two numbers, alpha, beta. I'll just plot it here. So this is alpha, and let's say this is beta. Okay. You'll see why we need these two 4 points to be noted here. Now, let's terminate this here. So at alpha, right, this is the point, right? At alpha, your u is alpha to the power p minus 1, right? This is this point, this particular point. And so let me draw this again. So let's, okay, so this is the point. Now, there can be two cases. One is when this value, right, alpha to the p minus 1, alpha to the power p minus 1 is greater than beta, right? Sorry, greater than beta, right? So to make it more clear, let me just connect this one and this one to make a rectangle, right? So you can see a rectangle. And in this situation, we see this increasing curve is above this value beta, right? At alpha, it's above the point beta, right? There's a height here. You can see there's a height here, right? What can be the other scenario? The other scenario is when you have the same thing, alpha, this is beta, and this is t, this is u. Let me connect this. What can happen is it's actually less than, right? So this point is alpha to the power p minus 1. It is actually less than beta, right? So these are the two scenarios, right? Either it can be above the point beta or it can be below the point beta. Well, it can also be beta, right? It can also have equal to beta. That's also possible. But let's look at these two cases, okay? So let me mark this. Okay. Now what do we need to do? We need to just do some geometry, right? So you just need to do some geometry to figure out this inequality. Well, it's interesting. How do we get this from geometry, right? Well, that's interesting. Just hold on. So let's look at this first case. Let me denote this as 1, this is 2. So what you see here is you see a rectangle, and the area of a rectangle is alpha times beta, right? So length times the width is alpha times beta. It is the area, right? But you can see there's another way to area, right? And that's by integrals. If you integrate this curve, right? Integrate this curve. So you basically find the area under this curve from the point 0 to alpha. Well, let me write this here. Integral 0 to alpha, right? What's the curve? The curve is nothing but t to the power p minus 1. So you just do t to the power p minus 1 dt. You integrate from 0 to alpha t to the power p minus 1 dt. And that's basically this area, right? What you see, what I have drawn here, right? And plus, you can also consider another area, which is basically, this second, right? The 2 that I've marked here. So basically, what I need to do is for every point here on the u, on on the u, let me say u axis, it's y axis, it's u, basically it's u. You basically need to find these heights, right? You just need to find the heights and then sum them or basically integrate them, right? So you need to integrate from 0 till beta, right? You're going from 0 till beta, right? You need to find these heights. What are these heights, right? Well, that's interesting. You can find out what these heights are by using some basic, algebra. Well, this graph, this curve is nothing but u is equal to t to the power p minus 1, right? U is t to the power p minus 1. So is it possible to find the t when you're given u, right? That's exactly what we're doing here. So you have a u here. Is it possible to find that corresponding t value, right? This height, right? Given a u here, say u1, is it possible to find that t1, right? That's basically the problem here. Is it possible to find that height? Well, you can. You just need to basically do u to the power 1 by p minus 1 is p, right? So you just need to do u to the power 1 by p minus 1. So p minus 1 divided by 1 minus p divided by p minus 1 cancels and you have t, right? So basically you're inverting it, isn't it? You're just inverting it. Well, 1 by p minus 1, interestingly, well, if you go up, we found something here. P minus 1 times q minus 1 is 1. Well, what does that imply? Q minus 1 is nothing but 1 by p minus 1, right? So 1 by p minus 1 is q minus 1. So what I can do here is basically 1 by p minus 1 is nothing but q minus 1. It's just q minus 1, right? So your t is nothing but u to the power q minus 1. Well, that's nice. You have the height t. Now, all I need to do is, so I know the height t, right? If you give me u, I know the height t. So now you integrate from 0 to beta, right? All these heights, basically find this area, right? Find the area here as well. So integrate 0 to beta. You just need to do u to the power q minus 1 du, right? Well, u to the power q minus 1 is basically t. You're basically integrating those heights, right? Well, you have two integrals, basically two area under the curves, right? You can, but if you just look at the figure, you can see that the area of rectangle, which is basically alpha times beta, which is here, right? Which is here, this much, right? The area under that, well, that's smaller than the sum of these two areas, right? Because you can see there's this portion here which is exceeding, right? Which is an extra portion, right? So basically you have this, right? This right hand side is greater than alpha times beta. Okay. Now it is the same thing here as well in the case 2, where you have this. So this is basically case 1, and this is basically case 2. Okay. So let me just erase some of these there. Okay, there you have it. So it looks nice. Okay, so for the case 2, it's the same thing. You need to integrate under the area, right? Under the curve, right? So what is the inequality that you have here? Let's try to figure it out. So you have integral 0 to alpha t to the power p minus 1 dt. This is t to the power p minus 1. Well, this is the same curve, t to the power p minus 1 dt. And then plus you have the other area, right? You just need to find these heights, which we found. It is nothing but it is nothing but u to the power q minus 1, right? We found it here. Okay. And you just need to integrate it. So plus integral 0 to beta, right? You need to do the 0 to beta, and you just need to u to the power q minus 1 du. Okay? Well, actually, when you have beta, so there's a small mistake here from my side. When you have beta here, your height is this, right? So there's an extra portion there. So there's that rectangle alpha beta, which has this area under this. This is the rectangle, right? But when you integrate from 0 to beta, u to the power q minus 1, you have this height, right? So basically at beta, your height is this. This is the entire height, right? So, and here, this is the entire height, right? So you have like an extra portion here, and because of which integral 0 to beta u to the power q minus 1 du, well, this is again bounded below by alpha beta because the area of that rectangle is smaller than the integrals, right? So in both the cases, you see this inequality holds, okay? So it just follows from this nice looking graph, right? Now let's try to integrate this. So this right-hand side, integration of t to the power p minus 1 dt is nothing but t to the power p by p, right? And you just need to evaluate the limits 0 and alpha plus q by q, and you just need to evaluate the limit 0 and beta, right? So this is nothing but alpha to the power p by p plus beta to the power q by q, right? Because when you plug in 0, it's just 0, it just vanishes, right? So you have alpha to the power p divided by p plus beta to the power q divided by q. The same thing here is the same integral. It's just for case 1, this is for case 2, but the integrals are the same. It's alpha to the power p by p plus beta to the power q by q, right? So, well, there you have it. That's the inequality that we need. Now, the only thing that we need is to prove. So what do we need to prove? We just need to prove this. We just need to prove this stuff, right? So you need to consider sequences, right? And let's consider 2 sequences. So you have this one and this one. Now, I'm going to assume something about these sequences. I will assume that summation, if you take this one, right, if you take the individual terms and if you raise to the power p, and if you sum all of them, right, it's equal to 1. Okay, so let's assume that these 2 sequences are such that this holds. So this is this other one to power q. This time it's q. Okay, it's 1. So if you know a functional analysis, you know that this belongs to the LP space. This belongs to the LQ space, right? Basically, what's the definition of LP, and LQ? That is, you have the sequence. When you sum them, you take individual terms, raised to the power p. It should be 1, right? If you have this to be 1, or it should actually be bound. I'm sorry, it's not actually 1. For this to be in LP, it's this stuff, right, to the power 1 by p. It should be just a finite number, right? It should just be. It should not blow up. It should be just less than infinity. That's the definition of LP and LQ. But well, we don't need to think about that now. All I need is I'm going to assume, right, that this falls. Okay, this is 1. Okay. Well, you can see that there are sequences like that, right? What's the trivial sequence? Trivial sequence 1. Everything else is 0, right? That does give you the summation j1 to infinity is 1. All right, so that's good. Now let's move on. How do we use this in proving the Holder's inequality? So what we can do now is basically, let's take the term, right? So this one, you just multiply them, take the absolute value. So I'm going to use this inequality here. This is bounded above by, and I'm taking the absolute value, right? So yeah, so because you don't need this to be positive, right? These 2 sequences, they need not be positive, but you can always take the absolute magnitude and make those terms positive. And when you multiply, this is bounded above by to the power e by p plus eta j to the power 2 by 2. Okay, you have this for jth term, right? Now this holds for every term, right? This holds for all j, right? Because this inequality holds for any number alpha beta. So I'm taking the positive numbers to the value of this j term of this sequence and j term of this sequence, and this holds. Now all you need to do is sum both sides, right? So when you sum both sides, what happens? Summation j 1 to infinity, summation j 1 till infinity, and that's also summation j 1 till infinity, right? So let me actually write it properly so that it looks good. You have plus summation j1 till infinite, eta j to the power q by q. Okay. Now we assumed that, well, 1 by p is constant. You can take it out, right? It comes out summation j eta j to the power p plus 1 by q summation j1 till infinity summation eta j to the power q, right? Now this is 1, this term is 1 because we assume this one, right? If you take the summation, it's 1. Here also the summation is 1. So what you're left with is 1 by p plus 1 by q, but 1 by p and 1 by q, by our assumption, this is 1, right? That's how we chose these two numbers. When you take 1 by p plus 1 by q, it's 1. Okay, good. Now, from here, what do we see? We see that summation j1 till infinite, absolute magnitude of this 2 is bounded above by 1, right? Okay. Well, how does that give us the Holder's inequality that we saw in the beginning of this video? Well, what you need to do is remember the LP space and LQ space, right? So you can pick sequences from here. Well, yeah, so you need LP and LQ space. What's the definition of LP and LQ space? It's just that sequence when you do this to the power p, right? Basically, this should be bounded. This should, when you sum this, right? When you take individual terms, raised to the power p, when you sum it, it should be just bounded, right? The same thing, summation j1 till infinity, eta j to the power q should be bounded. Okay, so hence these two are sequences from the LP and LQ space. Now what you need to do is let's construct a new sequence. How do I construct this? I will take the jth term and then divide this by this quantity 1 till infinity to the power 1 by p. Okay, well, we know that this is bounded, right? This is a number, right? Bounded means it's a real number. I can definitely take the 1 by pth root, right? I can definitely take that. And so I'm basically kind of like normalizing it, right? So you take the individual term, jth term, and divide by this term, right? The same thing, this new sequence can be constructed by dividing by summation j1 till infinity, eta j to the power q, the whole raised to 1 by q. Okay. Now, interestingly, if you take this one, what happens to the summation of j1 till infinity to the power p, right? What is this? This is nothing but j1 till infinity, eta j to the power p, divided by, well, when you raise this to the power p, what happens is summation j1 till infinity, summation j to the power p, right? So your p and 1 by p cancels, right? So it just becomes 1. Now, this is nothing but it's summation j1 till infinity, eta j to the power p, divided by summation j1 till infinity, eta j to the power p. Is the same thing, right? It's 1, right? It's the same thing for the other sequence, summation j1 till infinite to the power q, summation j1 till, well, you will see that it's the same thing. So it's eta j to the power q divided by summation j1 till infinite, eta j to the power q, right? So q and 1 by q cancels, and you have this term Well, this is, it will turn out summation j1 till infinite q, this is 1, right? So what that means is I can basically use this result, right? I can use this result, that summation j1 till infinity. When I do this, it should be bounded above by 1, right? Should be bounded above by 1, because you have this summation, absolute magnitude of this new terms, right? New sequence that we have created. Raised to power p, it's 1. Here also 1. So what that implies is summation. When you do this, 1 till infinity, it should be bounded above by 1. Okay? But what are these two terms? These two terms are nothing but eta j, and here you have, so you remember how we, so this is this one, right? This is how we constructed it, right? This is how we constructed it. So I'm just going to replace that there, and you will see this is j to the power p to the power 1 by p, and you also have the power q 1 by q, which is bounded above by 1. Well, every term, right? For every term, this is the same thing, right? For every term, j, eta j, this is there, right? This is constant. And no matter what j it is, the denominator is the same. Here also is the same, no matter what j is. So the whole summation, in the whole summation, these two are constants. You can actually pull that out. So summation j1 till infinity. This term is bounded above by, well, these two are just numbers. I'm just going to make it, take it to the right hand side. So you have this to the power 1 by p, summation j or q to the power 1 by q. Well, there you have it. That's the Holder's inequality. Well, amazing. That's the Holder's inequality. That's pretty interesting.